We spend our lives walking through, working in, and living inside these massive concrete structures. But have you ever really stopped to think about what's holding it all together from the inside? Okay, let's get into this, because there's this whole hidden world of precision engineering that makes everything possible, and it's pretty fascinating.
Just look at any construction site, any skyscraper, any bridge. They all seem so solid, right? So permanent. But their incredible strength doesn't just come from the concrete you can see. Nope, there's a secret, an invisible framework that's locked deep inside.
So what is this hidden skeleton? What's this unseen element that gives these colossal structures the power to basically defy gravity? Let's answer that.
The answer lies in this really clever concept of combining two materials to make something way, way stronger than either one could ever be on its own.
It's called rebar, which is short for reinforcing bar, and you should think of it as a literal skeleton made of steel that lives inside the concrete. This partnership is what gives our modern world its incredible world-shaping strength.
And this combination creates what we call reinforced concrete, or RCC. Think of it like a perfect team-up. See, concrete is amazing at resisting being crushed. That's its compressive strength. But it's actually pretty weak if you try to pull it apart. Steel, on the other hand, is incredible at resisting being pulled. That's tensile strength. You put them together and boom, you get a super material that can handle just about any stress you throw at it.
But, having a great idea is one thing. Actually, making it happen is a whole different ballgame. This presents a massive logistical challenge. How do you turn a complex design on paper into thousands of perfectly shaped steel bars on a busy construction site?
So here's the puzzle, right? How do you communicate the precise instructions for every single piece of that steel skeleton? We're talking exact lengths, specific angles, and a designated spot for thousands, sometimes hundreds of thousands of individual bars. How on earth do you manage all that?
Well, the answer is an elegant and, frankly, absolutely essential document. It's the master instruction manual for the entire structural skeleton.
The solution is called the Bar Bending Schedule, or BBS for short. And this document, it's the critical link between the architect's vision and the physical reality of what gets built on site.
As our source material puts it, the BBS is the indispensable process that bridges architectural designs with structural reality. And that's so true. Without it, all you've got is a drawing and a big pile of steel. With it, you have a concrete plan to build a skyscraper.
Okay, so what does this master document actually look like? Let's break it down. Let's look at the anatomy of a bar bending schedule.
I know. At first glance, it just looks like a really complicated spreadsheet. But this right here, this is the command center. Every single row in every column is a direct order for creating one specific piece of the building skeleton, from the very bottom of the foundation all the way to the roof.
And this is how you tame the chaos. Each column has a very specific job. It tells you the type and size of the bar, the exact length to cut it, the precise details for every single bend, how many of that bar you need, and exactly where it's supposed to go into the structure. It's basically a complete biography for every single piece of steel.
Let's just zoom in on one of those details for a second. The cutting length. This isn't just an estimate. It's a precise calculation that figures out the exact length of a straight bar before it gets bent. Getting this right is absolutely critical. It minimizes waste and makes sure the final piece fits perfectly. So let's just trace the journey of one of these bars. It all starts as a simple line on a structural drawing. That line then gets translated into a detailed set of instructions on the BBS. Those instructions then guide these powerful machines that cut and shape the raw steel, until finally you have the exact, finished piece all ready to be installed. And this right here is that connection in action. The abstract plan on the left, all the numbers and codes in the spreadsheet, is directly controlling the physical machinery on the right. Every bend, every angle is dictated by the data from the BBS. And this is the end result. What might just look like random piles of metal is actually a highly organized collection of custom fabricated parts. Each one of those piles is tagged and ready to be delivered to a specific part of the construction site, all thanks to the meticulous planning of the BBS.
All right, so let's zoom out to the big picture here. Why go through all this trouble? Why is the bar bending schedule so fundamentally important to modern construction?
Well, this table really says it all. Without a BBS, you have chaos. You've got wasted material from cutting errors, you've got conflicts on site, constant delays, and questionable quality.
But with the BBS, you get control, you get cost-effectiveness, you get accuracy, efficiency, and most importantly, you get quality, control, and safety.
So the crucial point is this. The BBS isn't just a document about bending bars. It's the project's central nervous system. It saves money, it guarantees safety, it creates clear guidelines for everyone on site, and it even serves as crucial documentation for the project. It transforms potential chaos into precise execution.
So next time you look at a skyscraper, remember the unseen skeleton and the master document that brought it to life. That's the power of the bar bending schedule. It truly is the indispensable bridge from design to reality. Kind of makes you wonder, what other hidden systems like this are quietly shaping the world around us?